We are going to learn the what we call the series solution method. So the series solution method, series solution method. So let's talk about some basic facts about this. So let's say we have a solution y which we write as a series. So in going from 0 to infinity, cₙx̅. So we assume this. So be a solution of the differential equation. So we have a differential equation. We try to find the solution of that. So we assume that this is the solution. So that means so we have assumed that the series converge on some interval. We assume that the series converges on a interval x minus a less than or at least. So we are, in this case you can see that a is equal to 0 when you write the series solution in this form. That's the form we assume for the moment. So here a equals 0 and then r can be positive or even infinity. So r can be positive, so even we allow the infinity. So what does that mean? So if you look at the situation, you can see, so that is the a and there's r, so that's the r, so it can go both direction, and that's the interval you are talking about. So this is the interval on which the series converge. X is somewhere here inside this interval. So that's assumption, and r go both ways. Good. And such a point, so if you pick a point on that interval, we call such a point is an ordinary point. So we talked about that earlier. So such points are called ordinary point. Ordinary points. So those are what we normally call ordinary points. The other points are where the series does not converge, or what we normally call singular points. Okay, that's for differential equations. So if you talk about any other context, it may be different. Good. And we also know from calculus that we can differentiate and integrate converging series. So we know that we can differentiate and integrate. We can differentiate and integrate converging series. And we also know something about that. When we differentiate or integrate, it doesn't change the radius of convergence. So this does not change. The radius of convergence. So in this case r, so it does not change r, but it may change. You don't say it will change, it may change, because there are certain situations it doesn't change. It may change the interval of convergence. because there can be issues with the endpoints. So that's why we say that it may change the endpoints. It may change the endpoints. So it can change the interval of convergence. So that was the situation, but that depends on the problem that we have. So what we normally do, every time we're going to check those endpoints to see whether the series converge at that particular point. So that's we need to do for such problems, endpoints. And then there are two questions. So when we have a power series, what's going to happen if you take a derivative of the power series? What's going to happen to the index? So let's talk about that. So let's ask this question. So what happened when differentiating a power series y equals sigma? We ignore the index, we say cₙx̤. So let's ask this question, what's going to happen? So for that, let's expand a series and see what's the situation. So what we can do, we can write the series in this form. So that's a series. We assume that n going to start with 0. So it is cₙx̤n. So if you write this as an expansion, what we can do is we can write the first term. That means when you apply n equals 0, you get the first term, and we write the rest as a series. So the next index is 1 to infinity cₙx̤n. Now what we can do, we can differentiate. So we can differentiate this with respect to x. We assume that we know that this is discrete, but what we can do is we can assume that this is continuous and consider only the discrete points. That's what we normally do, because we know that we can integrate or differentiate discrete functions, but we assume that it is a continuous function and only consider the point where the function is continuous. So we kind of picking points from a graph. So that's how we do. So we simply consider the whole function. So let's say this is your whole function. What we normally do is that's the function y. What we normally, we just take the derivative, that means we consider the slope, but what we do, we're going to pick the points only at those special values. So that's how we do. So whatever the x point, we're going to look at the value at that particular x point. So that's how we do. So that means we can still do the derivative. So there's a slope somewhere, and at that point, so we just pick that point. So that's the only thing. So so that's why we can take the derivatives that even like it looks like discrete functions, because we just focus on that particular point. Okay, good. So now what we do, we take the derivative. So differentiate with respect to x, because x is the variable. So you're going to get y prime, and then when you take the derivative of c0, it is 0. So that means that term going to go away, and inside what we can do is we're going to take, because we know that we can take the derivative series, so we just take the derivative. So it is cn times, when you take the derivative of xn, it's going to be nxn minus 1. So what we can do is we can write the n first, cn xn minus 1. So that's what happened, because we can take the derivative of the series part. But now what we can see, the first term is gone, so you only have sigma n going from 1 to infinity n cn xn minus 1. So what do you need to notice? You need to notice this part. The index change from n equals 0 to n equal 1, and also index change at the x power. So index of x change, we normally call this index or the power or the order. So there are a lot of names for that, but that change. So that's the what we notice. So let's do it again. So let's take the derivative of this one again. But again, before we do that, what we do, we write the first term. So let's rewrite this one like this. So let's have the first term. If you write the first term, you're going to get 1 times c1 x to the 1 minus 1, that means x to the 0. That's just a constant. So that means we can ignore that. So I'm going to erase this part. So that's the only one we have, because x0 is 1. We assume that even x equals 0 case, we assume that it's 1. So that's just a assumption. Yeah. Plus, let's try the rest. What's the rest? It's going to start with, because we write the first term, we have write with the second term. So n equal 2 to infinity, and then we have n cn xn minus 1. Now we take the derivative again. So for a future reference, I'm going to call this equation 1. That's where you take the first derivative. Good. Now let's take the derivative again. So differentiate with respect to x again. So you're going to see that y prime, as before, this is a constant, so it's 0, is gone. So, and then inside the summation, you can take the derivative. So it's going to be n minus 1 cn xn minus 2. As before, the first term is gone, so you only have n going from 2 to infinity, n minus 1 cn xn minus 2. So again, you notice that index change to the starting value with index change to 2, and then n, this becomes n minus 2 also, and also you have a extra term coming here. Good. So that means if you keep doing it, now you can see actually this is not the first derivative, it's the second derivative. So you can see y third derivative, which is equals to, now again the first term gonna go away, so you're gonna start with n equal 3 now, and then you can see n minus 1 and n minus 2 cn x to the n minus 3 now. So again, so you see that this change and that change. So that's exactly what happened. So I'm going to call these equations. So I'm going to call this equation number 2, and this is equation number 3. So these are useful for future reference. Okay, so that's exactly what's going to happen when you take a derivative. You can see how the index change, starting with n equals 0, it jumped to n equal 1, and jump to n equal 2, like that. Good. So we can use this idea again and again when you use the power series method to solve differential equations. So that's one more question. The other question is, we're going to see what happened when you set a series equal to 0. So let's look at that. So let's see what happened when we set a series. So let's say a series xn, we set this equal to 0. So this is like also a very interesting question. Okay, we can do that when you try to solve a series using the power series method. So the idea is, you know that, like now again earlier, so let's say we know that the functions, we know that the functions 1, x squared, x3, like that, are linearly independent. So this we know, they are linearly independent. We show that using the Wronskian or just by the definition. Now let's say we set a regular series equal to 0. So let's see. So now if you set the series n going from 0 to infinity, cn xn, in other words, if you expand this is like c0 and then c1x and then c2x squared, like that. We know that the c0 through c0, c1, c2, those are numbers, just numbers. So what we do, we set equal to 0. So that means if you just look at this part, so this is exactly the definition of the linear independence. You set a linear combination. This is what we normally call linear combination. So this is a linear combination. So it's linear combination, you set it equal to 0. So by the definition, because we know that those functions are linear independent, by the definition it says that, so this implies that the all those constants c0, c1, c2 like that are all equal to 0. So we can use that fact also when you try to solve a differential equation using the power series method. So yeah, so those are the two important things that we're going to use. So one is what happened to the index when you take the derivative, and the other one is what happened to the coefficients when you set a power series equal to 0. So in summary, what's going to happen, so if you set a power series, let's say the index start with 0, whatever index that you like, cₙx̅. So if you set this equal to 0, this is set. So you set this equal to 0, this implies that all the coefficient functions has to be 0 because those functions are linearly independent. These functions are linearly independent. That's the reason, linearly independent. Good. So let's see how we can use this in a problem. So we start with something easy. So let's say the first example. Find a power series solution. Find a power series solution. Find a power series. Find a power series solution. Find a power series solution. Y equals sigma. N going from 0 to infinity. cₙx̅. Power series solution of the differential equation. Of the differential equation. Of the differential equation y prime plus y equals 0. I mean, that's the easiest one that we can handle. So let's do the easiest first and see what's going on, and then we can do some harder ones. Good. So our assumption was, we assumed that the solution can be written as a power series. So that's a big assumption, but we assume that that's the case. Now what we're going to do for the answer, so what we're going to do now, so we're going to say so let's take first take necessary derivatives. So first take necessary derivatives. So in this case, you can see, you only see y prime. That means you only need to take one derivative. So as we did before, so you can just write it, but I'm going to show you the steps again just to make sure that we remember. So in going from 0 to infinity, cₙx̅. What we did, we write the first term and then we write the rest. cₙx̅. You can see that there's nothing changed on this, just the index is the only thing changed. Good. Now what we do, we take the derivative. So once you take the derivative, so this is that y prime equals, this is 0 because of c0, so it's gone, plus the rest. So the rest is sigma n going from 1 to infinity. Just take the derivative of the inside function. Cn is a constant, so it is n cₙx̅ minus 1. So that's what you get. So that means your final answer you can write as n going from 1 to infinity n cₙx̅ minus 1. So I'm going to call this thing equation 1. This is equation 2 because we need them later. Okay, now what we're going to do, we're going to substitute. We're going to substitute this in the differential equation. So substitute in the differential equation. So we can say star. So if you substitute, what is y prime? Y prime, so we start with, so it is y prime plus y. Y prime is this one, so we're going to substitute for that. So it is sigma n going from 1 to infinity n cₙx̅ minus 1 plus y. Y is the original series that we had, so we're going to say sigma n going from 0 to infinity cn xn, cn xn. But we know that by from the differential equation this is equal to 0, because that's given. This part is given. It's equal to 0. If it is equal to something else, just say that, like equal to x or something like that, sin x. That would be difficult, but it can be polynomial, so it's already equal to that number. Now the thing is that you can see they have different index now. So you can see here it's going to start with n equal 1, here it's n equal 0, and also we have different powers. So that means you cannot combine them, you can add them. So what we're going to do, we're going to use the seesaw argument to add them. So we use a seesaw argument now. So we're going to use the seesaw argument to rewrite using I'm going to say one index. Good. So let's do that. So we're going to use the seesaw argument to rewrite this using one index. So you can see what we need to do is, if you look at the second series, I'm going to call this first series and the second series is the first series and the second series. In the second series it is xn. So what you want to do is the first series you write as xn. So to do that, what you want to do, you can see that you want to bring this up by 1. That means you need to bring the index by 1 down. Okay, so up by 1, down by 1. So we can do that. So that means we can get sigma. So we're going to start with n equal, we can see that 0, because you bring it down to infinity, and you can see this become n plus 1. So n become n plus 1, and then c n plus 1 xn. That's what happened in the first one, plus the second one, no change, in going from 0 to infinity, cn xn, no change, and equal to 0. Now you can see that they are exactly the same powers, same index, so you can simply add them together. Good. So we can add them together. Once you add them together, you can see that you can write this one as c n sigma n equals 0 to infinity. We simply put them together. So that means it's going to be n plus 1, c n plus 1. We only write the index, and then this is cn, and then we write the common x term outside. Now this is set equal to 0, and we discussed this before. You can see that you set a complete series with some kind of index. That's the index now of the new series, just one index, the coefficient. Now you just set it equal to 0. So we know that this xn function is linear independent, so that means this coefficient has to be 0. That's the only option we can get, because this is equal to 0. So if this is equal to 0, because we set this equal to 0, so this implies that this coefficient term has to be 0, because those xn functions are linearly independent. And then you know that, so this is true for all x. Is true for all x in the interval of convergence. In the interval of convergence. In the interval of convergence. So it's true for all. So thus, the only thing that can happen is the coefficient function has to be 0. In this case, not the coefficient function, the coefficient has to be 0. In this case, it says that n plus 1 to the cn plus 1 plus cn has to be 0 for all n. So in this case, it is starting n equals 0. So that means for all n greater than or equal to 0, but positive integers, all the integers. So in other words, what we can do is we can divide. We can bring the cn term to the other side and divide by n plus 1. So this says that cn plus 1 is equal to negative 1 over n plus 1 cn. So you bring cn to the other side and divide by n plus 1. So and then you can see that this is true for all n starting with 0, 1, 2, 3 like that. So you call such a relation, we call this kind of relation is a recurrence relation. Why? Because you can apply the same relation again and again, so we call this a recurrence relation. So this is called a recurrence relation. Recurrence relation. This is called a recurrence relation. We use this a lot because you apply this repeatedly. So the goal is to find few terms. So just find a general expression for cn. So that's it. So we mostly done with this. So now what we can do, so basically let's plug in few values. Few values of n. So we can plug in few values, like we can start with n equals 0, 1, 2 like that, and we can find few values, and if possible we try to find a pattern. So that's the major thing. Okay, so let's do that. So let's start with plug in some values. So let's start with n equals 0. If you plug n equals 0, what do you get? You can see that it is n plus 1, this becomes c1, and minus 1 over 0 plus 1, c0. So if you simplify, you're going to get c0. So c1 is simply equal to negative c0. Now we're going to do n equal 1. If you do n equal 1, this becomes c2, and then again minus n plus 1, that means 1 plus 1, c1. So that means this is negative 1/2 c1, but c1 is equal to negative c0. So you can see that's negative positive, so you get 1/2 c0. So we always try to rewrite using previous ones, so we simplify as much as we can. And then n equal 2. If you do n equal 2, this is 3. So you can see that negative 2 plus 1 c2. We already know what the c2 value, so we're going to plug in that. So it's going to be negative 1/3 here, and then c2 is equal to 1/2 c0. So if you simplify, we normally don't simplify, leave it like that to find a pattern. So we don't simplify, we leave it like that. So c0, that's what you get. So it looks like we are getting factorial. If you look at these terms, it look like the 1 over factorial 2, 1 over factorial 3. Let's see. And then we're going to plug n equal 3. So if you plug n equal 3, so what's going to happen? c4 equal negative 1 over 3 plus 1 c3. We already know what the c3 value, so it is negative 1/4, and then we have negative 1/4, and then this is negative 1 over 3 2 c0. So if you simplify all the way, you get 1 over 4 times 3 times 2 c0. That's what you get. So that means now what we're gonna do, and you can see there's a nice pattern here. So if it is n, what happened? So and you can see if c2 is even, it's a positive one. If n is even, it is a positive term. If it is odd, if n is odd, it's a negative term. So you can see some kind of pattern here. So for example, so in general, so you can say in general, Cn is equals to, so it looks like negative 1 to the n over, in the bottom you can see it is factorial. So you can see it is factorial n c0. So what is factorial n? Factorial n means you can multiply n and then n minus 1 like that up to 1. That's factorial n. So that's exactly what we have here, because you can see so this is factorial 4, and you can see this is factorial 3, and this is factorial 2. That's hard to see, but when you look at other terms, you can see that that's exactly what's going on here. So that means in general, what happened, so we're gonna get that one. Now what we can do is we can go and plug in back into the original equation, because these are the coefficients, so we can plug in the coefficient. So so what we next what we do is we plug in, so we plug in this in the sigma, so because we just found the coefficient, so we're gonna plug in for the coefficients. We're gonna plug in for this, so let's do that. So you're gonna get y equal c0. If you look at the expansion, it's a good idea to write the expansion, or we can just write it here because we know the general expression now. But normally, like what we do in a regular problem, we write the expansion, plug in there. But if you know the general form, just plug into the general one, that's enough. But that will be difficult most of the time. So it is c2x² like that. So what we can do, we're gonna plug in here. So we find 4 terms, so let's write all the 4 terms. We have 4 terms now, so it is c3x3. We normally do that until we see a pattern. So it would be enough to write like maybe like about the first 3 or 4 terms. So let's plug in. So once you plug in, what happened now, you can see this is simply c0. c1 is equal to negative c0 x, and the next one is c2 is equal to 1/2 c0, 1/2 c0 x², and then negative 1/3 c0 x³, and then positive 1/4 3 2 c0 x4, like that. That's what happened in regular situation, and then we try to see whether there's a pattern. That's what we normally do. Now you can see each and every term has a c0 term, so we're gonna pull that out. That's common, so we can take it out. So once you do that, so you can see then y is equals to, simply if you pull c0 out, so you're gonna get 1 from the first term, x from the second term, and then 1/2 x² from the third term, like that, and then 1/3 2 x³ from the third term, plus like that 4 3 2 x4, like that. And then you can see that this is the coefficient term is simply written as power series using the factorial as we did before. So that means we can rewrite this one as c0. So I'm going to write just few because this is the first example. So you can see this is negative 1/factorial x to the 1, and then this is 1/2 factorial x to the 2. This is 1/3 factorial x to the 3, like that. 1/4 factorial x to the 4, like that. So that means in general you can see that this is simply c0 sigma n going from, so in this case you can see start with 0 to infinity, -1 to the nth power over factorial n x to the n. You can write it like that. And why we have a -1 to the n? Because you can see that the sign alternately change, so we need a so let's say since sign changes alternatively, we need a -1 to the n term, but you have to be careful, it should match. Sometimes it is -1 to the n, sometimes -1 to the n minus 1, so there are things like that, you have to match it. So in this case -1 n works because when you apply n equals 0, it's -1 to the 0, that is positive, that means that works with the first term. That's how we figure out that's the case. Okay, now we know that So by calc 2, this is simply the exponential function. So this is simply e to the negative x. So we can plug in that here. That's the series representation of the e to the negative x. So because of that, we can write this one as c naught e to the negative x. So and then you can get this value. So we use the table of common Maclaurin series. Common Maclaurin series. So you can find that in the basics of the power series video. So we gave a common tables there. Just you can use directly. Okay, so this is the solution. So and then you can see that if you use another technique, for example, this is like, we know this differential equation, we have solved this many times. So if you go back, so we know, so I'm going to write a note, and then you can see that the differential equation y prime plus y equals 0, this you can write as y prime equal minus y, and we know the solution of this one. So the solution of this one is normally given by y equal a constant e to the, in this case, k equal 1, so it is negative 1x. So that we know already, but this confirms that that's exactly the case using the power series method. The problem is there are many problems that you cannot solve exactly. So what we normally do is we try to find a series representation of that. In those cases, we might not be able to write in the closed form, but here we have another way to do it, but here the goal is to show you how it works. Okay, so let's do another problem. So this is the first example. So it's a good idea to redo it and until you clearly understand all the process. So let's do another one. So what we're gonna do is we're gonna do one with some kind of x terms in there. So how about this one? So the next example. So let's say solve y prime plus 3x squared y equals 0 using power series method. Using power series. So we can use power series to solve this. So the answer, so we're going to say suppose y equal sigma n going from 0 to infinity, cₙxn is a solution for an ordinary point x, so that means there is some kind of interval where that works. Now what we can do, so then we're going to take the derivatives, then we can write this one as y prime is simply as before sigma n going from 1 to infinity. So we can take the derivative, so it is n cₙxn minus 1. We don't need any other derivative, that's only what we need. Now what we can do by substituting, so by substituting we're gonna get sigma n going from 1 to infinity n cₙxn minus 1 plus 3x squared sigma n going from 0 to infinity, that's the original one, cₙxn. In the problem it is set equal to 0 because that is given. Now what we normally do is we're gonna bring this term inside, so we normally do that, and also we try to change the index. So let's first bring this term inside. So if we bring the term inside, so this n going from 1 to infinity, nothing changes, n cₙxn minus 1 plus sigma n going from 0 to infinity 3 cₙx. So what happened, we have x squared here, we have x to the n here. So what happened, you're going to add the 2. so it's going to be n plus 2 because you have extra x squared terms there, so at 2. Now you can see that they don't have the same x powers. So let's see what's going to happen in the x powers, because what we normally do is we're going to write the uncommon terms first and then the common term. So what are the terms that we're going to get if when you apply in the first value? So when you apply n equals 0, so you can see that this can be n equal start with n equal 1. So n equal start with n equal 1. When you apply n equal 1, this can start with n equals 0, x to the 0. And then when you plug n equals 0 in the other one, this can start with x to the squared. So you can start with x squared. So that means the first series has two terms which are not common. So we can write those two terms first and then write the rest of the terms. So let's do that, because there are two uncommon terms here, x to the 0 and x to the 1. Those are not common. So we can write them first. So that means we have 1 times c1 x to the 0 plus 2 times c2 x to the 1. Those are the two uncommon terms, and the rest we can write as a sigma. So now the first two terms are gone, so you can start with n equal 3 now. So that's the one. So start with 3 now, and the rest we write n c n x n minus 1, no change, plus we did not change the index yet, n going from 0 to infinity 3 cn x n plus 2 equals 0. Okay, now what we're trying to do, we try to change the index. So the goal is to rewrite this as xn. So that means you can see here what we need to do is we're going to bring this one down by 2. That means this one up by 2. Here this is going to be go up by 1, this one down by 1. So it's very clear, because if you do that, then you can see everything is in xn. So let's do that. So we're going to use using the seesaw method. So if you forgot about the seesaw method, you can look at the video and you can see the link in the description. So let's see what's going to happen. So we're going to see this c1 plus 2c2x plus, so let's bring it down by 2. That means it's going to be n going from 2 now, because you bring it down, and then inside you're going to increase by 1. That means this is going to be n plus 1 cn plus 1. Every n you replace by n plus 1. You just add a 1, that's it. Wherever you see n, add a 1. So it is n. If you add a 1, it's going to be x to the n, because you add 1, gain minus 1, jump by 1. Plus the same thing here, you're going to increase this one by 2. So that means it's going to be 2 now to infinity 3. You increase by 2, so cn plus 2 now. Actually it's decreased by 2. So it's not increase, it's decreased by 2 now, because it's going to go down. So it's n minus 2 and then xn equals 0. And then once you do that, you're going to see that this is xn, this also equal, so you can simply add them together. So you can do that. So what you're going to get is c1 plus 2c2x plus, just add them, so sigma n going from 2 to infinity. So we write the common, we just write the coefficients. So it is n plus 1 c n plus 1 plus 3 times cn minus 2, and we write the common power outside equal to 0. Now again, this is a series. You set this equal to 0. So this implies that, it's an argument, so we need to write these things. We can't just write numbers. Implies that all the coefficients are equal to 0. So that means this is equal to 0, this is equal to 0, and this whole thing here equal to 0. So we can do that. So this implies that c1 equal to 0, c2 equal to 0, these are equal to 0, and we have n plus 1 times c to the n plus 1 plus 3 c to the n minus 2 equals 0 for what? It's for, look at the index value, for n greater than or equal 2. Those are positive integers. Yeah, so that means, in other words, you can say if you divide by n plus 1 and bring it to the other side, you can write this one as c n plus 1 equal negative 3 over n plus 1 c to the n minus 2. So it looks like they are kind of some kind of factorial, because when you divide by a, when you multiply by n or n plus 1, a fixed number every time, it's kind of create a factorial term. Good. So this is true for n greater than or equal to 3, 2, 3, 4, 5, like that. Good. So that's the recurrence relation you're looking for. And then we also know the first two terms are 0. Now what we can do, we can write a few terms just to see a pattern. So let's do that. So let's see whether there's a pattern. So what we can do, we already know c1 and c2 are 0. So we know that c1 equals c2 equals 0. We know that those two are equal 0. So what we can do, we can start with the next value. So let's say what happens if you put n equal 2. With n equal 2, you're going to get c3, which is negative. If you just plug in n equal 2 in the formula, so it's going to be 3 over 2 plus 1 c0. In other words, negative c0. So we get, and then n equal 3. If you do n equal 3, you're going to get c4, which is negative 3/4 c1. And then we know that c1 equals 0, so this is 0. And then we do n equal 4, this is c5, so this is negative 3 over 5 c2, but we know that c2 is also equal to 0, so this is 0. So let's do one more, n equal 5, so this is c to the 6. Just find few numbers until we see a pattern. So it is 3 over 6 c3, but we know what is c3. c3 equal negative c0. So when you plug in that, so what are you going to get? A negative 3 over 6. So we are not going to simplify, we leave it like that, because otherwise we can lose the pattern. So I'm going to leave it in the original form. So it is 3 over 3 c0, actually negative, so I forgot the negative sign. So let's put that back in. So it is negative 3 over 3 c0. So if you simplify this all the way, so it's going to be you can see negative 1 2 times, and then we have 3 2 times, and in the bottom you have 6 times 3 c0. There is a kind of pattern, and let's keep doing it. So n equals 6, so we do n equals 6, you get c7. So c7 is negative 3/4 c4, but we know that this is equal to 0, so that's gone. And then n equal 7, you're going to say c8, which is negative 3, actually not 3/4, this is 3/7. So 3/7, and this is 3/8, c to the 5, and we know that the 5 is also 0, so this is also gone. And then let's see n equal 8, so you can see 9, which is negative 3 over 9 c6, but we already know what is c6, so let's plug in. So it's a negative 3 9, and then we have negative 1 to the second here, and we have 3 squared over 6 times 3 c0. So if you rewrite this one, you can see negative 1, now you multiply 3 times 3, you get the cube. In the bottom you're going to see 9 6 3 c naught. So so you can see that we only get the powers of 3. So you get 3, 6, 9, and everything else is 0. So it might tells you something. So we may be able to rewrite the general term. So let's write the general term. So what's the general term look like? So you can write for n equal 3 to the k 3 to the k, k going from 0 1 2 3 like that. So you can see it is so let's write it. So you can see it is c to the 3k, that's the term look like. It is negative 1 to the k, and then you have 3 to the k over what we have is 3, 6 like that, and then we have until 3k term c naught. So this is valid for k going from this is valid for k going from even from 0. No, we have 3k, so it's going to 1 2 3 like that. So let's see how we can simplify this, and then how many terms we have. We can see that there are k many terms. There are k terms. So how to simplify this a little bit? So what we're gonna do is, you can see from the terms in the bottom, you can pull 3 from each. So once you do that, you're gonna get 1 times, 2 times, 3 times like that to k, and also you have 3 to the k term from each. So once you do that, and then c naught, you can see that 3k and 3k get cancelled. So you simply get something like this. You're going to get negative 1 to the k, 1 over 1 2 3 up to k c naught, but that's just a factorial, so that means be negative 1 to the k over k factorial c naught. So that's what happened. Actually, we could have seen this earlier also if you simplify this one, but sometimes that's really not a good idea. So that's the reason why I did not do that, because sometimes we lose the pattern and then it's really hard to figure out what's going on here. So now, so we know the general term, so let's write the form. So what happened now? So thus, so we can say y which is equal to n going from 0 to infinity. So you can see we only get the terms with a power of 3. So we don't get anything. We only get c to the 3n x 3n, because everything else is gone because they are all 0. So those are the only terms that we get. That's why we only write these terms, the multiples of 3. So but we know that according to this formula, so you can use k or whatever index you like. So in going from 0 to infinity, so you can see you can substitute that, so it's a negative 1 to the n over you can see n factorial and then c naught x to the 3n. Yeah, x to the 3n. So now what we can do is we can pull the c naught out. So if you pull the c naught out, you're going to get c naught times, you're going to get n going from 0 to infinity. So we can do some kind of nice simplification here. We can write this one as, this is simply equals to x to the cube of n. So we can do that. So if you do that, then what's going to happen? This term simply going to be negative 1 to the n over n factorial. This is going to be x to the cube of n. So once you do that, and you can simply see that this is simply c0, that's the, so this one is a power series, so this is simply e to the negative x cube. So you can see this is simply e to the negative x cube. That's the power series of that. So that means that's going to be the solution. So the solution is simply c0 e to the negative x cube. So if you look at the graph of this one, what kind of graph you get? So this is the negative powers. So this is simply going like the, whatever the c0 values, it's going to go like that. So that's the c0 value. That's the c0 value. So that's the graph of the function we get. And also, so we get the final answer in the closed form. That's hardly happen most of the time. And you can see that you can also solve this problem using a separable method. So I just do this as a recalling what we did earlier. But this confirm that we get the same answer. So for example, so I'm going to say not. So the problem. So let's say we use a separable method. So if you use the separable method, so the problem is y plus 3x squared y equals 0. We're going to separate them. So what we normally do is we're going to write this one as dy by dx, and we're going to bring this to the other side, negative 3x squared y. We're going to bring the y terms to one side, so we can write this one as dy over y negative 3x squared dx. Now what we do, we can integrate two sides. Once we do that, you can see this is simply ln y. This is equal to ln absolute y equals to negative x3 plus c, and this implies that y equal, we have done many simplifications like that. This simply implies that c0, that's not the same c0 e to the negative x3. So that's exactly the same solution. And also we can solve this also using the integration by parts. I'm sorry, integrating factor method. So we use the integrating factors. So if you use integrating factors, we can see this y prime plus 3x squared y equals 0. So the integrating factor is simply e to the, so that's the p function, that's the px function. It is integral of px dx. So in this case it is e to the integral of 3x squared dx. That's very easy to integrate, so you get e to the x cube, and then you know that what we do next is we write dy by dx, y times the integrating factor, which is equal to 0, and then once you integrate, what's going to happen, you're going to get y e x to the cube is a 0. That means you get a constant, let's call it c0, and you can see that once you divide both sides by e to the x cube, you get y equal c0 e to the negative x cube. So it's also exactly the same answer. It should be. Solution does not depend on the method. So you can see this is the same answer, but in this case, so it's confirmed that that's exactly what we get. But there are some problems it's not that easy to do, but still we can find a series solution. That's exactly why we learn this, because this is like we are learning the technique. But for these kind of problems, you really don't need that. We can just either separation of variable or the integrating factor method. But I want to tell you, like, we get the exact same answer even doing that. Okay, so we solved two problems. So let's solve two more. Now let's try to go to the higher order case. So what we're going to do, we're going to do second order differential equation. So let's solve a second order differential equation. So the next example, solve y double prime minus 3y equals 0. Again using a power series method. Using power series. And again, this problem, this is a constant coefficient differential equation, so we know how to solve this one. But let's see how the power series, and also this is coming from 4 formula. Remember, 4 fundamental equations. This is one of them, so we already know the solution of this one. It has the we can see the cos and sin. So let's see what's going to happen now. So we know that, so I'm going to write a few things about this just to make sure that we know what's going on here. So this is a constant coefficient differential equation. So this is a constant coefficient differential equation. So that means all the points are ordinary points. So all the points are ordinary points. And then we know that there's a theorem which says that if it's an ordinary point, there is a series solution, and so you can say and a series solution exists, and series solution exists. So that means we can do what we're trying to do, because sometimes you cannot do that. There's no solution. So if you're trying to find such a solution, is not a valid thing to do. So what we can do, we can assume as before. So let y equal sigma n going from 0 to infinity cₙx̤ be a solution, and then we know that the y prime, so you can say then y prime is simply n starting with 1 to infinity. You simply take the derivative inside, so n cn x n minus 1, and then you can see y double prime is start with n equal 2 to infinity n minus 1 cn x n minus 2. Okay, now what we can do, we can plug in these 3. Actually you don't need 3, you only need y and y double prime. We plug in them in the equation. So substitute in 1, substitute in the equation. So substitute in the differential equation. So we're gonna get, so let's see what we're gonna get. We're gonna get sigma n equal 2 to infinity n minus 1 cn x n minus 2 minus 3 times the original one, so it is n going from 0 to infinity cn x n equal 0. Okay, so we need to change the index, and you can see that xn is already xn, so we need to get the xn here. That means we need to up by 2, down by 2. So we can do that from the seesaw method. That's exactly what you need to do. Very easy. You're gonna inside you gonna increase everything by 2, and outside here you decrease by 2. So let's do that. And also I'm gonna bring this 3 inside, so this one you can bring inside. So let's do all of these, so see what's gonna happen. And then also we can write so it is sigma, we're gonna say n going from, we're gonna go down by 2, then we're gonna 0 to infinity, and then we have, so we increase, so n gonna be n plus 2, and then we have n minus 1 is gonna be n plus 1 because you add 2, n becomes cn plus 2, and x is going to be xn, n minus 2 going to be xn minus sigma n going from, okay, it's just 2, no, it's not 2, it is 0, right? That's 0. and then this is 0 already to infinity. So we pull 3 inside, and 3 cn xn equals 0. When you combine, so we can write this one as sigma n going from 0, because you can see they are all the same. See, the same term, same index, so you can just add them, just simple algebra. So we can have n plus 2 n plus 1 cn plus 2 minus 3 cn xn 0. So this says that this has to be 0, because that's the only possibility that we can have. This has to be 0. So we can say then, or thus, we have n plus 2 n plus 1 cn plus 2 minus 3 cn equal to 0 for what value? N starting with 0, 0, 1, 2, like that. So look, I'm a little faster than the computer, so it doesn't detect my writing. Okay, so let's solve for cn plus 1 plus 2. So you divide by, so you can bring to the other side and divide by that. So it's going to be 3 over n plus 2 n plus 1 times cn. Now what we can do, as before, we're going to plug in the values and try to find few values. So let's do that. So let's start the first value. So let's say 4 n equals 0. You're going to get C2, that's what you get, which is 3 over, so you can put n equals 0. So it is 2 times 1 times C0. Good. And if you simplify this a little bit, you're going to say 3 over, I'm going to write it 2 factorial, it looks like, but let's see, C0. And then for n equal 1, we normally don't do that until we see a pattern, but let's see. So it is C3, so we have 3 over, so you add 2, so it's become 3 times 2 C1 now. So we don't know what is C1, so we can leave it. So it is 3 over 3 factorial, it looks like, C1. So again, n equal 2, whatever n equal 2, so you're going to get C4, which is 3 over 4 times 3 C2. Actually, we already know what is C2, so we can plug in for that. So that means it is 3 over 4 3 times 3 over 2 factorial C0. So that simply coming from here, and you can see, you can simplify this, so you're going to get 3 squared 4 factorial C0. So they get actually not 4 squared, C4, so much we get, yeah, good. So let's keep doing it. So let's find a few more values just to until we see a pattern. So you can stop whenever you see the pattern. So let's go for n equal 3 also, so that you're going to get C5. So you're going to get 3 over 5 times 4 C3. We all know what is C3, so it is 3 over 5 4 times 3 over 3 factorial C1. So you can see that this is 3 squared over 5 factorial C1, and then we have n equal 4 C6. So you're going to get 3 over 6 times 5 C4, and as before, so this is 3 over 6 times 5, and the C4 is 3 squared over 4 factorial C0. That means you simplify all, you get 3 cube over 6 factorial C0. And as the last one, let's say n equal 5 C7, so it is 3 over 7 6 C5, so this is equals to 3 over 7 6 C5, which is equal, so let's plug in C5, so this is going to be yeah, let's plug in C5. What time already? So the C5, so we're going to plug in for C5. C5 is 3 squared 5 factorial C1, and if you simplify this a little bit, so you can see 3 cube 7 factorial C1. So you can see in general what's going to happen now is you can write such a Cn, because for odd numbers you get one pattern, for even numbers you get another pattern. So you can see every time you have a factorial, so few things that we can notice it, this number and that number match, and so you see those numbers match, so that's one thing. And for even powers it's go with C0 for even, for odd powers it's gonna go with C1. So we notice those two. And what is the power? So you can see first set go with 3 3, and then 3 squared, and then 3 cube. So that means that is the number that you use to write odd even numbers, because we know that if you have a odd even number, so like an even number you can write as 2k, and odd number you can write as 2k plus 1 or minus 1 depending on how you want to write it. Because since we start with C0, this would be better to write, so they can start with k, can start with 0 1 2 3 like that. So that means because of that, so that k is the one giving the power. Because for example, if you write 7, how to write 7? So 7 is equal to 2 times 3 plus 1, so that's the k value. So that means you can see that that k value is the one goes up there. So because of that observation we can write, so in general, so if you solve the formula neatly, we normally do that, but in a normal situation like in a quiz or exam, we don't go up to that far. We probably ask you to write first few terms, but this is a kind of good practice. So you can see in general Cn you can write in two different ways. So one way is it is 3 to the k over 2k factorial C0, that's when n is even. And then the other one is 3k, you can see 2k plus 1 factorial and C1, that is when n equal 2k plus 1. So that means for odd and even, and then k ranges from, for all of them, k ranges from k goes from all the way from 0 1 2 like that. So that's the general form of the Cn term. And then after we know that, now what we can do is we can plug in that in the formula. So we can do this in two different ways. First, like just plug in the values and write the form that we normally do, so we can do that. So we can say thus y, what we can do, we look at the expanded form, so it is C0 plus C1x plus C2x squared, like that. So we're going to plug in there. So let's plug in few values that we found. So it is C0 that we just leave, C1 we just leave, and then starting C2, now we know the value, so it is 3 over 2 factorial x squared, and the next term is 3 over 3 factorial x to the cube, and then like that, and then we have a 9 over 4 factorial x to the fourth, and then plus 9 over 5 factorial x to the fifth, like that. So and then what we can do is, what we normally do is, so we can take the odd powers and even powers separately. So if you take the odd powers and even powers separately of this, your y can be written as y equal, we're going to pull the c0. Let's say if you write odd powers, so if you write odd powers, what you're going to get 1 plus 3 over factorial 2 x squared. Oh, this is even powers actually, so I write 9 over 4 factorial x to the fourth, like that, plus c1, the odd powers, so we have x plus 3 over 3 factorial x to the cube plus 5 over 5 factorial x to the fifth, like that. So what we normally do is we're going to consider this as one function. This is one function y1, and this is the other function y2. So if you call them y1 function, y2 function, then you can write the solution as c0 y1 plus c2, it's not c2, c1 y1. So those are the two functions, and you can see that they are linearly independent because of the different powers. So that's the general solution. And also we can do a little bit more here. So let's notice something. You can see using the general form that we had, so this is good enough, so you can write it like this, and then here you can see, let's say here y1, actually this is not y1, this has to be y2. Good. Here y1 and y2 to linearly independent functions. Good. But we can do a little bit better in this case, because sometimes like you get really nice solutions. So you can see that your y, you can write using the general form. So the first one you can write as sigma. It was k going from 0 to infinity. What was that? What's the general term? It is 3 to the k 2k factorial x to the 2k. These are only the even powers, plus c1 times sigma, again k go from 0 to infinity, 3 to the k, and the odd power, so it is 2k plus 1 factorial x to the 2k plus 1. So what else we can do? And we can see that we can bring this 3k term inside here. So the same thing, we can bring this 3k term inside. So let's try to do that. So the goal is this, and we know that so we can write x to the 2k as x squared to the power. So we can write x to the 2k as x squared k. So we can do it like that. So that's one way. And also we can write 3, you can write 3 as 3 square root squared. That's what we need for our case, because then we can pull the 2 out. So if you do that, then you can rewrite this one as c0 sigma k going from 0 to infinity. So you can rewrite this one as 1 over 2k factorial, but not 2k factorial, you can write this as square root 3x to the 2k. Can write like that, because 3 square root squared, so we pull the 2 out. Once we pull the we can, because 3 is square root squared, so with the k it becomes 2k, so we can pull the 2k out and do the same thing. But for that, what I'm going to do, I'm going to multiply and divide by 1 of the square root, because there's a 1 left there. For that we need extra 1. For the extra 1, what I'm going to do, I'm going to multiply by extra square root 3. So if we do that, so you get c1, and then we're going to put that extra square root 3 term here, and then what we can do, we can rewrite the rest like that. So it is sigma k going from 0 to infinity 1 over 3k plus 1 factorial. I'm going to bring the 3k power inside, so it's going to be x to the, again, square root 3x. So I'm going to erase this now. So we have, so you can write this one as, now it is the whole thing 2k, but you have this extra 1, so I'm going to add that, so plus 1. So that's the what is the extra 1? There's extra square root 3 that going to cancel with that square root 3, that's that extra 1. So we can write it like that, and then you can see this is simply the cos function and the sine function expansion. So that means if you look at the table, you can see this is simply c0 cos square root 3x plus this is c1 over square root 3, that's still just a number, sin square root 3x, as we know. So that's exactly what we expected, because we already know this solution. So we can say as expected, because we know that's the solution from the constant coefficient differential equation method or for fundamental equations. So but we surprisingly we exactly get the same solution for this one. Yeah, so that's what so that's the final answer for that, and we know how these kind of functions behave. And c1 or square root 3, you can just say c1, just a number. Okay, so let's do one more. So let's do one with the x term. So how about that? So because this is a constant, so let's do one with x term. So so the next one, so we have like plenty of examples. You can learn all the tricks how to handle these kind of functions. So we can do 2 more examples, one with the x, one with 2 terms and one with 3 terms also. So let's say solve y double prime minus x y equals 0, again using power series. So as before, so I'm going to write the just theory part first. So let's say any x in the real numbers, any real x is an ordinary point. It's an ordinary point because the functions, first coefficient is 1 and the next one is negative x. Those are all analytic, so that means every point is a ordinary point. We know that those functions are, if they are analytic, then the points are ordinary points. So so there is a power series solution. So there is a power series solution y equals sigma n going from 0 to infinity c and x, and centered at, we're going to add few more now, centered at x equal 0, that converges for let's say x minus 0, which is exaggeration, less than some kind of r. Yeah, good. Okay, so and then we know that we need to take the derivatives now. So we can start with y equals sigma n going from 0 to infinity cn xn. This implies that y prime is equals to sigma n equal 1 to infinity n cn xn minus 1, and y double prime equals to sigma n equal 2 to infinity n minus 1 cn xn minus 2. Good. So we again notice that the 3 index 0 1 2. Okay, so now what we do, we're going to plug that in. So by substituting, yeah, this is kind of slow. Okay, by substituting, we have y double prime minus xy. We only need to plug in for 2 terms, so let's do that. So this is sigma n equal 2 to infinity n minus 1 cn xn minus 2 minus x times y. So this is n going from 0 to infinity cn xn. So now one thing that we can do is we can put the x inside. That's the first thing we do. So that if you do that, then you're going to see that sigma n equal 2 to infinity n minus 1 cn xn minus 2 minus sigma n going from 0 to infinity cn xn plus 1. Okay, now what we're going to do, we're going to rewrite using one index. So we're going to add 2, we're going to bring down by 2, again we down by 1, up by 1. Then you can write everything using x to the n. So it's very clear now. So if you do that, and also and actually I forgot, we said this equal to 0, so this is simply equal to 0 equal to 0, but we still need to write using first one index. That's why we are waiting. And what terms you get actually, if you apply n equals 1, n equal 2, you get x to the 0 here. If you apply n equals 0, you get x to the 1 there. That means there is a one uncommon term. The uncommon term is coming from the first series. So let's write the uncommon term first and then write the other two series. So we write the first uncommon term. So let's write the first uncommon terms, that is 2c2, and then we can see that the first series is going to start with n equal 3 now. So it's 3 to infinity n minus 1 cn x n minus 2. You can see that there are no change for those yet, and then plus sigma. It's not a plus, it's a minus. So minus sigma n going from 0 to infinity cn x n plus 1, which is equal to 0. Now what we can do, the index change. So you see that this has to go down by 1, up by 1, up by 2, down by 2. So let's do that. Once you do that, you're gonna see you're gonna get 2c2 plus this one gonna change n going from 1 to infinity. So and the inside we're gonna increase by 2, so it's gonna be n plus 2, and then this one gonna be, you add 1, so n plus 1, and this will be cn plus 2. This is xn. minus sigma. This is increased by 1, so it's going to be n equal 1 now to infinity, and then you can decrease by 1, so see n minus 1, this is xn equals 0. After we do that, you can see that these are all match and this also match. Okay, so that we can combine them into 1. So once you combine them into 1, you can rewrite this one as 2c2 plus 1 sigma n going from 1 to infinity. You can see that n plus 2 n plus 1 c n plus 2 minus c n minus 1 x to the n equals 0. Now we know that this is a power series. You set it equal 0, that means all the coefficient has to be 0. So this says that this has to be 0 and also this term has to be 0. So this gives we can see c2 equals 0, and we can set this one equal to 0, so it's n plus 2 n plus 1 c n plus 2. You can see minus c n minus 1 equal to 0. That's valid for n equal 1 2 3 wherever the series start. The series start with 1, so that's the first value they're going to start with. Now we know, like, we can solve for that. So this says that c n plus 2 equal c n plus 2 equal c n minus 1 divided by n plus 2 times n plus 1 is again n going from 1 to 3 like that. So what we can do is we can find first few values. Okay, so for n 1 2 3 like that, we have for n equal 1 we have c3 which is equal to c0 over, just by n equal 1, so you're going to get 3 times 2, and then for n equal 2 you're going to get c4 which is c1 over 4 times 3, and then for n equal 3 we're gonna get c5 which is equal to c2 over 5 times 4, but we know that c2 equals 0, that means this is 0. So keep doing. Let's find few more. So if you find few more for n equal 4, we're gonna get c6 which is c3 which is c3 over 6 times 5. C3 we already know, so it is 1 over 6 times 5 times 3 times 2 c0. And similarly n5 you're gonna get c7. Sometimes it's really hard to find patterns, so it is c4 over 7 times 6. c4 we already know, so we can plug in that, so it is 7 times 6 times 4 times 3 c1, and we find one last one, n6, so you'll say c8 which is c5 over 8 times 7, but we know the c5 is 0, so this is 0. So now what we can do is we can substitute that. So substituting So you can substitute, then we can see that the y equal c0 plus c1x plus c2x squared plus, so let's write few, and then c3x3 plus c4x4 plus c5x5 plus. So let's see the pattern. So you can see that some of the terms, for example c2 is 0, so this is 0, and then also c5 is 0, and then like that. So and then if you substitute from coefficients, so this is simply equals to c0 plus c1x and then we have a 0 plus we have c0 3 times 2 to x cube, and then we have c1 4 times 3 x to the 4th, and we have a 0 plus c0 6 5 3 times 2 x to the 6, like that. So what we're going to do, we're going to combine, we're going to separate them into c0 terms and c1 terms. So if you get the c0 terms, what are you going to get? You can see that you're going to get 1 plus, what's another c0 term? So that's the c0 term, and that's the next c0 term, and that's the next c0 term. So let's write them together. So you're going to get 1 over 3 times 2 x cube plus 1 over 6 times 5 3 2 x to the 6th, like that. Those are the c0 terms, plus the c1 terms are x plus 1 over 4 times 3 x to the 4th, like that. Good. And then yeah, you can have one more term. So the next term would be 1 over 7 6 4 3 x to the 7, like that. Now you can see these two are the two functions that you are looking for. So we're going to call this is y1 and that is y2 and that is y1. So if you do that, then you can write your solution as c0 y1x plus c1 y2x. So this is the solution of the equation. So sometimes it can take some time. There are like little complicated problems. So yeah, so I would like to do one more problem from this one. That's the last problem that I'm trying to do, and that is little lengthy, but we can still do it. So let's see how it's gonna work. So as the next example, we're gonna do, so this is the last example we're gonna do in this. So example, so let's do a 3-term equation. So solve, let's say x squared plus 1 y double prime plus x y prime minus y equals 0. So let's do that. So the first is, what are the origin point? So let's say, because we need to know where the solution exists. So the singular points, we know by the theory, singular points are the solutions of x squared plus 1 equals 0. So that's simply the coefficient of the largest term. So you can take the coefficient function and set it equal to 0. That's going to give the singular points, because you can divide by that. So thus x equal what? Plus or minus I are singular points. So you know that those are all complex. So that means if you pick a any other point, those are all ordinary points. So what we can do, so we can see thus x equals 0, which is not equal to this, is an ordinary point. Okay? Is an ordinary point. So what we can do, we're gonna look at the solution near that point. Is an ordinary point. So you can see, let's look at the graph of this. So where are those points? So you can see, if you look at the graph of this, if you try to plot these 2 points, and you can see one I is there, the negative I is sitting there. So those are singular points. That means you cannot touch these points. So what we can do, we can look at a circle which does not pass through those points. So what's the largest possible such circle? So you can see you can have a circle with exactly a radius 1. So it's touching that. So we can have a circle, largest circle with radius 1, then it's not going to touch. So what we can do, because if you start with 0, you can go up to 1, but not including 1. So you can say it's an ordinary point with radius. How far you can go? 1. With radius r equal 1. Okay. So the reason is, you can see x minus 0, how far you can go from 0 until you touch those singular points? You can only go 1. So that's going to give you where the solution exists. So what we try to do, we try to find a solution on that disk. So you can find any solution within that in this domain. So that's where we're going to find a solution, but you cannot pass that points. Okay, good. So let's do that. So now what we can do, we can assume a solution of this form, because there's a power series solution in that. Okay? So assume y equals sigma n going from 0 to infinity cₙxⁿ is a solution. I'm going to call this is star. Okay, is a solution of star. Now everything is exactly the same. Just take the derivative, plug in there, try to write using one series, power series, set it equal to 0, and everything else is the same after that. But this is like kind of a little bit tricky because we have a singular point now that we did not discuss before. Yeah, so let's try to finish the rest of the problem. So we're going to take the derivatives and plug in. So and then this implies that then we have y equals sigma n going from 0 to infinity cₙxⁿ, then y prime equal sigma. This can start with n equal 1 to infinity, take the derivatives is n cₙxn minus 1, and then y double prime, which start with n equal 2 to infinity. We have n minus 1 cn xn minus 2. Good. Now what we can do, we can substitute that. So we can substitute into the original equation, substitute into star. So if you do that, then you're going to get x squared plus 1, that's the first coefficient, and then y double prime, we're going to substitute the series, so the sigma n equal to infinity n minus 1 cn xn minus 2 plus x times the second series, we start with n equal 1 to infinity n cn xn minus 1 minus the last one, which is n going from 0 to infinity cn xn. We know that this has to equal to 0 because that's what's given. The next step is we're gonna distribute this. We're gonna bring those x terms inside, so we can bring the x term inside, and here we can use the distributive property. We can write 2, not just 1. So we're gonna bring this inside, that's true, but we can write 2 instead, because 1 for x squared, 1 for 1. So let's do that. So if you do that, then you're gonna get 2 series. So by the distributive property from the first one, we're gonna start with x squared term. So if you go with the x squared term, you're gonna get so let's see. So if you're gonna go with the x squared term, you're gonna get sigma n going from 2 to infinity n minus 1 cn, because since you have x squared term, xn minus 2 become xn now. So that's interesting. Okay, and then we have 1 for the plus term, plus 1. So for the plus 1, you're gonna get sigma n going from 2 to infinity n minus 1 cn xn minus 2. And then the other one again, we're gonna bring the x inside. Once you bring the x inside, this is n going from 1 to infinity n cn xn, and the last one is sigma, you can see n going from 0 to infinity cn xn equal to 0. Yep, it's a long expression. Now what we can do, we can check what's going to happen in each case. So if you do substitute few values, so I'm going to write again. So what we normally do is now write the uncommon terms, leaving common terms in the summation, leaving common terms inside the summations. Good. So let's do that. So if you do that, let's see what are the uncommon terms you get. So let's say when you apply n equal 2, you get x squared here. When you apply n equal 2, you get x0 here. When you apply n equal 1, you get x1 here. When you apply n equal 0, you get x0 here. So what's the largest term you get? So the largest term you get is x squared. That means we need to write everything up until x squared. So you don't have to do anything with the first term, but from the second one you have to write 2, from the third term you have to write 1, and from the last one you have to write 2. So let's write them. So if you write them, what we're gonna get is from the second one you have to write 2. So that means it's gonna be 2 times 1 c2 x0, that's the first term, and then also plug in the next value. So that means 3 times 2 c3x to the 1. So those are the uncommon terms from the second one. And then we write just one term from the third one. So what do we get? We get by n equal 1. So it's 1 times c1 x1. So that's the only uncommon term. That's from the third one. From the fourth one, we have two uncommon. This is a minus. So the uncommon one, when you apply n equals 0, that means c0 x to the 0, and then minus c1 x to the 1. So those are all the uncommon ones. Now let's write the common ones as a sigma. So so that means there's a common one from the first one. So n going from 2 to infinity, n minus 1 cn xn. Well, that's a common one, n equal 2. And then here you can see that x0, you have to leave the first 2 index because that's already gone. So you have to start with the third index. So that means it's 0. So you have 2 and 3, so you start with 4. So 4 to infinity, n minus 1 cn xn minus 2. Now what we're going to do, we're going to go to the next one. You have to write one term. That means you have to start with n equal 2. We just write 1. So it's n cn xn. And from the last one, you have to go with 2 index. So that means 0 and 1 is gone. So you start with 2. So if you do that, then you're going to get cn xn equals 0. Good. So those are the common terms and uncommon terms. And see what's going to happen. You can see some terms get cancelled. So this term get cancelled with that. I think that's it. Everything else gonna stay there. And now what we can do, we're going to see how to change the index. So you can see that you need to write using xn. To do that, xn is already there. So you can see this one, you need to go up by 2, down by 2, and then you can see it's already xn, so we can leave it there. So only we have to change only one of them, just one. So let's do that, and also rewrite all the terms that we already have. So rewriting like that, then we can have we have 2c2, and then we have minus c0 plus 6c3 6c3x. Those are the only the uncommon terms, and the rest we can rewrite using a common index. So first change the index of that one. So we're gonna see that plus, yeah, there are a lot of writing here. So I'm gonna write them in the, let's write this as a first term, n equal 2 to infinity, n minus 1 cn xn. That's simply coming from here, and then plus here we need to bring it down. So you can see sigma n equal 2 to infinity. Inside you're going to up by 2, so it's n plus 2, n plus 1 cn plus 2 xn, and then plus, no change, so n equal 2 to infinity, n cn xn minus sigma n going from 2 to infinity cn xn equal to 0. Now you can see they all have the same index, same starting value, and the same powers. So they all have the exact same power. So you can combine everything into one. So let's do that. So when you combine everything into one, so you can see that c2 minus c0 plus 6c3x plus sigma n going from 2 to infinity So let's combine them. So you're gonna have n plus 2, n plus 1, cn plus 2 minus, no, plus, actually a minus, I'm sorry, it's a plus k, not k, n. So we're gonna have 2c2 minus c naught plus 6c3x plus you can see sigma n equal to infinity. We have n plus 2, n plus 1, cn plus 2 plus n minus 1 cn, and then we have plus k, the k, n cn minus cn, everything x to the n equal 0. We can simplify this a little bit. For example, you can combine these two, and you can, after we do that, then you can combine the rest. And then we're going to combine all three after that. So first combine these two, and then because once you combine the first two, you can see that this is n minus 1 cn. Now what we can do, we're going to take n minus 1 from the last two. So when you do that, this last three, all of these you can write as n plus 1, n minus 1 cn. You can write like that. Okay, so using that, then we can write the final one like this: 2c2 minus c naught plus 6c3x plus sigma n going from 2 to infinity. We have here n plus 2, n plus 1, cn plus 2 plus n plus 1, n minus 1, cn, everything x to the n equal 0. So that's what we get. Now what we can do, as before, we can set the coefficient equal to 0. So this coefficient has to be 0. Also this coefficient has to be 0, and this one has to be 0 separately. Okay. So this implies this implies 2c2 minus c naught equal to 0, and then c3 equal to 0, and the expression, and we have n plus 2, n plus 1, cn plus 2 plus n plus 1, n minus 1, cn equal to 0 for n going from starting value is 2. So 2, 3, 4 like that. But you can see this term get cancelled with that, so we don't have much left. So this says that so this gonna give you what? So this gives from the first identity, you can see that c2 equal 1/2 c0, that's what you get. And then also c3 equals 0, and then here cn plus 2 equal, you can see negative n minus 1 over n plus 2 cn. This is valid for n going from 2, 3, 4, like that. Okay, so that means we can find the first few values. So let's find first few values for that. Good. Substituting n equal 2, 3, 4, like that. So we can see you're gonna get c4, which is negative 1/4, c2, and then for c2, c2 is 1/2 c0, so you're gonna get that. And then do the same thing, you're gonna say c5 is negative 2/5 c3, but we know that c3 is 0, this is gone. And then c6, which is negative 3/6 c4 we already know, so once you plug in that here, you're gonna get 3/6, 4 and a 2 c0. And then you can see c7, which is 0, like that. Okay, so we can find first few terms. Now what we can do, we can substitute them in the formula. So thus y equal c0, c1x, c2x squared, c3x3, c4x5, c4x4, and then c5x5, like that. But you can see some terms are 0. So for example, c3 is 0, so it's gone. c5 is 0, it's gone. So those terms are gone. So what you have is just a few terms. So let's see what you're gonna get now. So let's write it. Then you're gonna get c0 plus c1x. c2 is 1/2 c0 x squared, and then c4 is 1/4 times 2 x to the 4th, and then c6 is 3/6 times 4 times 2 x to the 6th, like that. So you can see we can separate the even powers and just one term. See, this is just one term here, and then we can isolate that, and we can combine all the other all the terms with the c0. So we're going to isolate, we're going to change them, so we can write them as terms with c0. It's going to be 1 plus 1/2 x squared minus 1/4 times 2 x to the 4th plus 3/6 times 4 times 2 x to the 6th minus, like that, plus we have c1x term. So what we're going to do, we're going to call this function y1. So if you call y1x, then you can write this one as simply c0 y1x, and I'm going to call this function y2. This x is simply y2, so you can write this one as plus c1 y2x. So this is valid on this is valid on x less than 1. Okay, so you have a solution which is valid on this range, this domain. So this is how we kind of do a problem, but you know that there are some problems which are a little lengthy, but this is just the general idea about how to solve problems using power series method.